Hello everyone, and welcome back to another episode of Total Organic Chemistry. This time, we're taking a look at electrophilic aromatic substitution reactions. After watching this video, the questions that you should be able to answer on your own are: how does a general electrophilic aromatic substitution occur? And how do I add halide, nitro, and sulfonate groups to benzene? If you'd like some review on general aromatic compounds, please go ahead and subscribe, and click on the video at the top of the screen before continuing. The most general form of an EAS reaction is this here. So we can start with a very simple aromatic compound like benzene, and then we're going to react this with a general electrophile. And I'm going to represent that electrophile as just E+ right now. And that is going to give us this substituted benzene compound, where we still have the aromatic ring, and we've just replaced one of these hydrogens with the electrophile. So remember, that is why it's called a substitution reaction, and benzene does not very easily undergo addition reactions like we might have with normal alkenes. So I'm going to draw out the mechanism for this reaction using the generic electrophile, just E+, and after that we'll take a look at some ways to actually generate different types of electrophiles. So the first step we have here is starting with our benzene. We will have our electrophile come in, and we know that there's some extra electron density in the aromatic ring, so we have those pi bonds coming out of the plane of the ring. So we can draw one of these pairs of electrons coming out of the benzene ring and attacking the electrophile here. That is going to give us this intermediate, where we have the electrophile and a hydrogen on the same carbon here, and we've broken the aromaticity of the ring, so we no longer have conjugation throughout all 6 carbons. And since one of these pi bonds broke, we're going to be left with a positive charge on the adjacent carbon here. And it's good to note that this positive charge is delocalized throughout the ring. So we've talked about delocalization in conjugated systems before, and we can draw some resonance structures to show that. So if we move this pi bond over here to the positive charge, then we can have another resonance structure where the positive charge is now on the opposite carbon of the electrophile. And we can draw yet another one, where we flip this pi bond over here to give the positive charge on now this carbon adjacent to the electrophile. Now this delocalization is going to make this intermediate stable enough to give us time for the next step to occur. And if we remember that this hydrogen is still on the same carbon as the electrophile, we can have some base come in and pluck off this hydrogen, and I'm just going to draw the bond from the hydrogen to the carbon coming down to reform a double bond and restore aromaticity in the ring. So that is going to leave us with the substituted product, where we now have the restored benzene ring, and we have one of those hydrogens is now replaced by the electrophile. And it doesn't matter too much the identity of the actual base that's taking off that hydrogen. Usually it's just going to be the most basic thing that we have in solution. Like I promised, now let's take a look at some ways to actually generate different types of E+ in our reactions. We can start with halogenation, which will be similar but not the same as our halogenation reactions of regular alkenes. So we can start with benzene again, and we are going to use elemental bromine, so just Br2 as our source of bromine, but we're actually going to need a Lewis acid catalyst in order to get this reaction going. So just treating with bromine is not going to do anything to the ring. So instead we can use, like I said, a Lewis acid like iron 3 bromide here. And as we'll see in a second, this is going to allow the substitution reaction to occur, and we're going to get the substituted aromatic ring with one bromine on one of these carbons. Okay, so what is the mechanism for this? Well, we'll start with our Br2 molecule, but this isn't going to be electrophilic enough to undergo substitution. So instead, we're going to take our iron 3 bromide catalyst, and this molecule and others similar to it have an empty p orbital, and that empty p orbital is going to accept electron pairs, so therefore this molecule is a Lewis acid. So what's going to happen here is one of the lone pairs from the bromine on the bromine molecule will come in to attack that iron atom here. And what we get now is this Lewis acid Lewis base adduct, where that bromine atom that lent its lone pair to the iron now has a positive formal charge. And we also have this iron center. Now that it has 4 bonds, it's going to have a negative formal charge. At this point, we've created a much more electrophilic bromine atom, and that's going to be this one that I've underlined here. So now we can have our benzene come in, And from here it's going to be a very similar mechanism to the one we just discussed. So we will take one of the pi bonds in the benzene ring, attack this bromine here, and then the bromine-bromine bond will swing up to the bromine to form a lone pair. So then we get our broken aromaticity, so we will have this ring here with the positive charge on this adjacent carbon, and then the bromine and the hydrogen on this carbon. And remember, now we need some sort of base to take off this hydrogen and restore aromaticity, and we can take this iron compound that we were just using, and this bond between bromine and iron can come over to take off the hydrogen, and then swing these electrons down to the ring to give us our final substituted product, and also regenerating that iron 3 bromide catalyst. So in this sense, it is a true catalyst. You only need it in small amounts in order to get this substitution reaction going. One thing you should remember is that the positive formal charge on this bromine in the previous step does not mean that it is the most electrophilic atom in the structure. Remember that formal charges are simply a formalism that allows us to keep track of where electrons are in a structure, but we need to think about where that electron density is to actually determine what is electrophilic and what is nucleophilic. Finally, I've shown this reaction occurring with bromine, but we can also chlorinate an aromatic ring using chlorine and some Lewis acid. We can also use something like aluminum trichloride or iron 3 chloride for the same purpose as this iron 3 bromide. Another substitution reaction we can perform is the nitration of benzene, so adding a nitro group or NO2 to this aromatic ring. And the way we can do this is take our benzene ring again, and we're going to treat it with nitric acid, HNO3, and this is going to be done in concentrated sulfuric acid. So we have this mixture of two acids. And like I said, this is going to add a nitro group to our benzene, so we will just substitute one of these H's with NO2. Okay, so how do we generate our electrophile here? So this is going to be done through the dehydration of nitric acid by sulfuric acid. So if we look at our nitric acid Lewis structure, we'll have this nitrogen center, and we'll have 3 oxygens surrounding it, and one of these oxygens will have a hydrogen as well. And if you notice here, we will have a positive formal charge on the nitrogen and a negative formal charge on this other oxygen. So then we will have our sulfuric acid come in, and I'm just going to abbreviate this with SO3H for the rest of the structure. And sulfuric acid is much more acidic than nitric acid, so it's going to be able to protonate this oxygen on the nitric acid, giving us this next intermediate, where we have the same basic structure, but now we have this oxygen on the nitric acid with 2 hydrogens, and for that reason it's going to have a positive formal charge. So then we can notice that this is essentially water, which is a pretty good leaving group. So the lone pair in this other oxygen on the nitric acid can come down to form a double bond with the nitrogen, and at the same time this will kick off the water molecule. This is why we call it a dehydration reaction. And that gives us our actual electrophile that we're going to be using in the EAS reaction. And this is going to be called a nitronium ion. Then, just like before, we go through the same steps for our general EAS mechanism. So we will have the pi bond in the benzene come in to attack that nitrogen, and at the same time one of these bonds will swing up to one of the oxygens, giving us this broken aromatic ring again. And again, we'll need some sort of base to take off this hydrogen. In this case, the most basic thing will probably be the water that we just produced. So we can have this water molecule come in, take off the hydrogen. Just like before, this bond will swing down to the ring to restore aromaticity and give us nitrobenzene, which is our substituted product. The last reaction I'll talk about today is the sulfonation of benzene, so adding a sulfonate group. Just as before, we'll start with benzene as our starting material, and we're going to treat this with what's called fuming sulfuric acid, which is very concentrated sulfuric acid with sulfur trioxide gas dissolved in it. So we have this SO3 and H2SO4. And this is going to undergo EAS again, and it's going to add a sulfonic acid group, which is SO3H. The mechanism for this is a little bit simpler than the previous one. So sulfur trioxide will be our primary electrophile here. And since it's in a solution of concentrated sulfuric acid, we can take our sulfuric acid here, and again we're going to have sulfuric acid protonate the sulfur trioxide. So one of these lone pairs in the oxygen is going to take that hydrogen from the sulfuric acid, and that's going to give us this protonated sulfur trioxide molecule. Now because of that positive formal charge on the oxygen, the sulfur is going to be very electrophilic here. So we'll have the benzene ring come in again. One of these pi bonds will attack the sulfur atom, and at the same time, one of the pi bonds in this double bond will come up to the oxygen to form a lone pair, and that gives us this intermediate. Exactly the same as before, we will need some base to take off this hydrogen, and in this case we'll probably have water again in the reaction. Although it is concentrated sulfuric acid, there's always going to be some water in there, and it's by far going to be the most basic thing in solution. So that will remove the hydrogen, restoring that aromaticity again, and giving us the final benzene sulfonic acid product. Now this reaction is interesting and important because it's actually reversible. So if we start with benzene sulfonic acid, and instead of treating it with this very concentrated acid solution, we can react it with dilute aqueous acid, so I'll just write H3O plus here, as well as heating it up, and that will reverse the substitution reaction, giving us just benzene as a product, and then sulfuric acid as a byproduct. So that allows us to use sulfonates as sort of a protecting group with these benzene rings, and we might come back to that in a later video. So I hope this video gave you a good introduction to electrophilic aromatic substitutions and how to generate some of these electrophiles. Please go ahead and like the video and subscribe to the channel. Follow me on social media, and if you're able, consider donating to my Patreon page, which helps me to continue creating all this content for you. Thanks for watching.